Okay, welcome everyone. Thanks for coming to our colloquium this week. Here we have today my longtime colleague and dear friend, Dr. Spencer Gessner. I'm going to read his official bio so I don't screw anything up, even though I should have this memorized. So Spencer is an assistant professor of particle physics and astrophysics at SLAC National Accelerator Laboratory in Stanford University. He was previously a staff scientist at SLAC, where he did research in plasma Wakefield acceleration at the Facet 2 facility, where we collaborate. He was also a fellow at CERN on the Awake proton beam-driven plasma Wakefield acceleration experiment prior to that. Professor Gessner earned his PhD from Stanford University studying the acceleration of positron beams in plasma, and he's currently coordinating the US 10 TeV Wakefield Collider design study, and is broadly involved in research on future colliders from the Higgs factories to the future energy frontier machines. So he's a real expert in this area. He's worked on this and thought about this for a long time. He's been a leader, I would say, in the field of thinking about these advanced designs for future HEP particle colliders. And as was hinted at in his little bio there, has a special expertise in the area of accelerating positrons, which is potentially very important for a lepton collider of the future. So without giving anything further away that might be in his talk, let me just hand it over to Spencer.
Thanks, Mike, and thanks for the opportunity to present here at CU Boulder. On this slightly inauspicious day, I hope I can be somewhat of a distraction. Okay, so as Mike mentioned, I'm going to talk about future colliders. But I'm going to start by talking about the place where I first met Mike, where we started working together. So this is an aerial view of SLAC. You can see the Klystron gallery above ground. And there was this facility called Facet that operated from 2011 to 2016. It was the first 2/3 of the copper linac. And so basically what we have is an electron gun, and then a lot of accelerating section, and then some special magnetic chicanes that help us to control the longitudinal properties of the bunch, make it very short in time and very intense. We have a way of making positrons. Making positrons is a bit messy. You smash electrons into a target, you make a spray of particles, you have to collect them, bring them back to the start, damp them, and then re-inject them. That's a whole big process. And then we have this final experimental area where we further compress the beam, focus it down in size, send it into a plasma, and then send it through some diagnostic section. So that's what the facility looked like. Here's what it looks like if you're working in the tunnel. So you've got the electrons or positrons coming 2 kilometers down the pipe. And we have a laser system. The laser system is upstairs above ground, but we pipe it down through a series of pipes and through a compressor chamber, through some optics, and onto the beam line. And then we have this box here, which is our plasma. So the plasma, it is a hot lithium vapor. We use lithium because lithium is an alkali metal. It's relatively easy to ionize. But there's also a challenge, which is, how do you confine a hot lithium vapor? And the answer that we came up with is you use a cold buffer gas. A cold buffer gas that's very hard to ionize. So when this particle beam comes through, it ionizes only the lithium, but not the buffer gas. And so we were getting ready to do some experiments in our hot lithium plasma, but we didn't have it on at the time. We just had buffer gas in the area. And the operators were tuning the beam, and they started to see these charge loss and radiation signals. And they made this somewhat snarky comment in E-log, ionizing helium, guess the beam is too good, sorry. And so this was a bit of a surprise. Based on what we could diagnose about our beam, we didn't think it should be able to ionize helium. We didn't think it was intense enough. But okay, we said, okay, that's interesting. Maybe we'll take a little bit of time just to study that effect before we move on to the real experiment. And so we had some time in the control room, and we were filling this cold buffer gas. So at 2 torr of background buffer gas, we have, it's missing this is an energy spectrum. So this is a waterfall plot. So each one of these lines is a different shot, and this axis is the energy. So the beam comes in at 20 GeV energy. Everything to the left is energy loss. Everything to the right is energy gain. Okay, so at 2 torr, everything's just losing energy. At 4 torr, everything's losing energy. At 8 torr, everything's losing energy. And at 16 torr, all of a sudden, huge jump in energy. And my French colleague, Sebastian Corr, who wrote this book, said, "Wow!" Very exciting time in the control room to see an effect like this. I mean, the effect is massive because we're sending in a 20 GeV beam, but we're actually getting out close to 50 GeV electrons. And so then we can zoom in on the 16 torr case. This is what a single shot looks like. You basically collapse along this axis to make each one of these lines, and you can make a spectrum, and you can see that your original particles had this energy, some of your particles gained a whole bunch of energy, and then you do some analysis about where you think this ionization was occurring, over how long it was occurring, and you get a number like 150 gigavolts per meter accelerating field. That long copper linac that we had the aerial view of, that's a 20 megavolt per meter accelerating field. So we're talking about an increase of a factor of 7,500. So that's basically why we're excited. It's the opportunity to take this giant machine and shrink it down to something that would fit in this room. The rest of this talk is going to be about some of the challenges of doing it. Okay, but before we get there, I need to talk a little bit about the future of high-energy colliders. So last week, Caterina Vernieri from SLAC came here. She told you a little bit about our push for the Higgs factory. And I'm going to talk a little bit about what comes after the Higgs factory. Okay, so we did this big community exercise called SNOMAS and P5. So 1,000 high-energy physicists from across the US wrote some letters of intent. COVID happened, so SNOMAS 2021 became SNOMAS 2022. We gathered in Seattle with all of our white papers to discuss these ideas. And that all filtered into this panel of experts called the P5 panel. And it was basically their job to come up with what it is the high-energy physics community is supposed to do over the next decade or two. And they said two things that's relevant to people who are interested in colliders like myself. So they said, we should pursue a Higgs factory, but actually someone else should pursue a Higgs factory. So the key word here is offshore. So really it means CERN, but possibly the ILC in Japan. So FCC at CERN, ILC in Japan. And we should help. And then they said, we're interested in this 10 TeV energy frontier. 10 TeV is sort of what's needed to move beyond what's going on at the LHC. And they have this funky unit, parton center of mass. So for those of you who are aware of the LHC, it's a 14 TeV collider. So it kind of sounds strange to say that 10 TeV is somehow beyond 14 TeV. But the point there is that protons are made out of constituent particles that collide around 1 TeV, 2 TeV center of mass, whereas 10 TeV parton center of mass could either refer to a 100 TeV proton-proton machine, where the particles inside the protons are colliding at 10 TeV scale, or electron positrons, muons, colliding with their full energy at 10 TeV. Okay, so there were a lot of colliders discussed as part of this SNOMAS process. So let's do a broad overview of what the possibilities are. So first thing, it's good to point out, a lot of people in the high-energy physics community often lament, we're not building any new colliders. We sort of are. We've got this high-LUMI upgrade, which involves a lot of collider innovation to take the current LHC and increase luminosity by a factor of 10. So new magnets, new techniques at the intersection points using these things called Crab cavities. There's a lot of new technology that's going in there. We also have a new collider in the US, the electron-ion collider. So this is a nuclear physics machine, but it's doing a lot of really interesting physics of colliding electrons with ions and studying the structure of protons and nuclei. This is actually a really interesting and challenging project from an accelerator perspective. Okay, so now let's talk about the future. So the first possible path is what I refer to as the CERN path. So what CERN wants to do is they want to build a new machine called FCC, 100 kilometers in circumference, and have this operating sometime in the 2040s. It's a Higgs factory. So colliding electrons, positrons at 250 GeV energy to study the Higgs boson. And then they want to follow that up with another machine called FCC-HH, which is colliding protons at 100 TeV center of mass. And the main, so first of all, CERN has some credibility. CERN has some credibility, one, because they're operating a giant collider right now, and they're clearly motivated to pursue a new collider. And two, they've sort of done this before. So before the LHC, there was a machine called LEP, which was an electron-positron collider. It's big ring, 27 kilometers. And then they upgraded it to the current LHC. So this has sort of been demonstrated. Still, there are massive challenges, but this idea kind of works. But what a lot of people are sort of skeptical about is the long timeline, 2060s, 2070s. You're like, I don't know if I want to stick around for that long. So, both at CERN and in the US, there's this push for another technology, and it's called the muon collider. It's a hugely innovative technology because you're colliding these particles that don't exist for very long, so that's a real challenge. And the idea is that you could get to 10 TeV parton center of mass before this 2060 to 2070 timescale. But there's a ton of R&D needed. In fact, basically for the rest of the things I'm going to talk about, there's a lot of R&D needed, but certainly a lot for the muon collider. Okay, another option, and this was also mentioned in the P5 report, is to build this machine called the ILC. It's a linear collider. It uses superconducting RF cavities. It's pretty long. It's sort of, depending on what energy you want to study, anywhere from 20 to 30 kilometers long. But that's, let's say, smaller than a 100-kilometer tunnel for FCC. So there's a bunch of people in Japan who want to build this in Japan. And there's a bunch of people who think that maybe actually CERN should build this at CERN as an alternative to this guy. I forgot to mention one thing. There's also a Chinese proposal for a circular collider called CEPC, which potentially could be built faster for less money. So that's another force that exists in this space. Okay, so one question about this linear collider concept is, if you built this, could you then get to the next energy scale? So if you build the FCC, you get to the next energy scale by going from electron-positron to proton-proton with high-field magnets. If you build the linear collider, can you get to 10 TeV parton center of mass? And that's basically what we study are these plasma colliders. So use the existing infrastructure and then upgrade it with a new accelerator technology to get us there. The time scale is still kind of long. Okay, and then there are sort of things that weren't covered or were discussed in P5, but for one reason or another, didn't make it into the final recommendations. But the world is kind of a crazy place. We should consider other options. So here's a few other options that are interesting. The first is C cubed. Katarina talked about it last week. So it's less expensive than the ILC. It probably has higher energy reach. There's interest in developing this cold copper technology in the US. This could be a possible option. There's an even more compact version of a Higgs factory, which is called XCC. It's a gamma-gamma collider. So you can actually collide photons to make Higgs bosons. It's also based on this cool copper technology, and it's developed by my colleague Tim Barklow at SLAC. And then there's a sort of a new kid on the block, which is called HALF. So it's a half plasma Wakefield accelerator, half normal accelerator for positrons as a Higgs factory. And I'll talk about this a little bit more later. And then finally, there's an upgrade path as a future 10 TeV gamma-gamma collider that I'll also discuss. Okay, so given all these options, is the HEP field organized? Do we have a clear plan, a clear mission? And what I'll say is that there really is a zoo of options out there. We got circular and linear colliders, 5 flavors of collisions. We've got electron proton for the ion collider, E plus E minus, proton proton, muon muon. Yeah. So there's a lot. So how do we think about all these options? All right, so as part of the SNOMAS process, I was on this thing called the Implementation Task Force. And we were basically supposed to look at all these different collider concepts and make some recommendations. And you need metrics. So metrics could be technical readiness, cost, size, complexity, power consumption, environmental impact. I think probably one of the most important metrics is called luminosity per power. And this is basically how much physics you can get out of your machine for a given amount of input power. And so we're interested in operating at these higher centers of mass. The circular machines cannot provide luminosity at higher centers of mass, but the muon colliders certainly can. And the plasma colliders, because we're using these very small beams, can also get high luminosity at high center of mass. But these schemes require a lot of R&D. And after we put this, recommendations out in the world, it became clear that really the only thing that people care about in the short term is technical readiness. What can we build now? And that still is actually the important question, because we really do want to build a Higgs factory quite soon. So technical readiness clearly is the most important factor. but that shouldn't, let's say, distract us from our long-term goals and the R&D needed to get there. Okay, so I mentioned the P5 recommendations. There were 3 paths to 10 TeV. I also talked about them at that last slide, but let's just go over really quickly what some of the technical challenges are. So proton-proton collisions at 100 TeV. So like I said, the LHC, CERN, going from LEP to the LHC has kind of already demonstrated this path. The challenges here are the 16 Tesla dipole magnets that will be needed. They're going to have to be either using this kind of, I don't want to say traditional niobium tin technology. It's still a new technology, but it's we know it's very expensive and hard to industrialize. We're talking about a $50 billion machine if we just kind of simply extrapolate along those lines. If we could come up with like a new high temperature superconductor that could, get us there, that would be huge. So we really need an excellent R&D program on studying new materials, and that could be a game changer. That's one option. High radiation environment, also another real challenge. This has to do with the sort of the cross sections for proton-proton collisions sort of level off, and you just get a lot of radiation into your detectors and things like that. Okay, muon collider. Very exciting idea. The challenge is that muons decay. So you have to capture the muons and cool the muons before they go away. So ionization cooling is the main topic, where basically you send the muon through a material. That material absorbs energy from the muon, so it cools it, but then you reaccelerate it. You add energy back only in one dimension, and the net effect is that the transverse phase space of the particles is reduced. The transverse phase space, though, we also refer to it as the beam emittance. So the volume of the transverse phase space is the beam emittance. And this scales well to high energy because the muons live longer due to relativity at high energy. There's also some like weird problems like neutrino radiation, which, okay. All right, and then Wakefield acceleration. That's what I'm going to talk about for the rest of this talk. There are a lot of challenges. Mike mentions positron acceleration being a big one. There's interesting nonlinear QED effects at the collision point. But these machines have the potential to be much more compact than other options. So let me dive into this in 1 second. So I'm going to talk about plasma colliders, but there's actually 3 Wakefield technologies that are pursued in the US. So P5 said, yeah, we need an end-to-end design concept using these Wakefield technologies. So we've got structure Wakefield accelerators, which are pursued, stewarded by Argonne National Laboratory, beam-driven plasma at SLAC, and laser-driven plasma at Berkeley. And what I want to say here is that, so we have this advanced accelerator R&D program. It's this DOE GUARD program. And so we say that it's stewarded by these laboratories, but in fact, there are many institutions across the US that are directly contributing to work at these laboratories or doing their own innovations. And Mike's lab here at CU Boulder is an excellent example of that. Okay, so let's talk a little bit about plasma acceleration. I'm sure you've heard some version of this before, but I'll go over it quickly. So, okay, these set of plots come from Robert Arianello's thesis. So Robert was Mike's student, graduated in 2022. His thesis is really an excellent reference. And for my new students, I actually have them read this because it's so clear and well written. But anyway, so basically what you got is you got a beam that's propagating into a plasma. And the plasma responds by making a wave, a density perturbation. And you can derive just just a simple harmonic oscillator with some sort of driver term. So you have this sinusoidal behavior of the wave. And if it's a cold plasma, there's actually no dissipation. This just lasts forever. And then to go from a plasma perturbation to a plasma field, it's a slightly complicated equation. But actually, if we just want to talk about the longitudinal dimension, it's just the derivative of the plasma perturbation. So if this is whatever, sine-like or cosine-like, then the field is cosine-like or sine-like. And by the linear regime, we mean that the beam creating this wake in the plasma is a perturbation on the background plasma density. Okay, so the thing that's nice about the linear regime is that you have these really well-behaved sinusoidal fields. So you can accelerate electrons or positrons more or less the same. But the thing that's bad about the linear regime is that the fields vary away from the axis. And you'll never have a beam that's completely on axis. It has some transverse extent. So if it's sampling fields from different parts of the wake, then you have this inherent energy spread of the beam, which you can't correct. So what we really want is something where all the particles in the beam can gain energy at the same rate. And nature gives us something, I don't know, lucky, or it just works out that there is a way to get there in the nonlinear regime. So in the nonlinear regime, the electron beam is denser than the plasma. It creates this plasma bubble. So the plasma electrons kind of zoom around this thing, and the plasma ions are this kind of heavy stationary background. They provide a linear focusing force. It's uniform inside of here. So this is a beam propagating to neutral plasma. Said all that. Okay, so what are the characteristics of this wake that are important? So, like I said, we would like all of the particles in the wake to gain energy at the same rate. So we can summarize these as different equations describing the wake. So the first equation has to do with something we call beam loading. So basically, particles at different longitudinal positions in the bunch see the same accelerating field. And we can create that by judiciously choosing our bunch parameters. Second, linear focusing. So the fields are radially focusing, and they're linear. They're linear because you have this constant background ion density, and linear focusing forces preserve the emittance of the beam. Particles at different longitudinal positions see the same focusing field. They're basically, if you're at the front of the bunch or the back of the bunch, you're seeing the same transverse focusing due to the ions. And particles at different transverse positions, so radially, if they're offset, the field is the same. So they gain energy at the same rate. Okay, so in this sense, a plasma accelerator operated in the blowout regime is ideal. It gives us all these four conditions. So I'm going to then go on to talk about where this model sort of breaks down a little bit for us, and some of the challenges we run into trying to accelerate positrons. So first, we want to then take this remarkable technology that clearly can be used to accelerate particles to very high energy, and something that we can control and accelerate bunches of particles with low emittance, and turn that into a collider. So what do we have to think about? So I found this talk from Keith Panofsky. He was the director of SLAC, and he attended one of the early instances of this advanced accelerator concepts workshop. So that's the main workshop for our community in Madison, Wisconsin in 1986. And he kind of gave the concluding seminar. What do you have to think about in order to build a collider? And his slides are online. His transparencies are online. And what he wants you to know is that it's a very interconnected problem. And what I can say, having worked on this topic for a little while, is that from our sort of R&D technology development perspective, we don't think about this. We have not struggled with the hard problem of fitting the pieces together and understanding the trade-offs. So this is the real challenge now. Okay, so P5 said, get your act together, form an honest-to-goodness design study, figure out how the pieces fit together, and then come up with a proposal. So this is a schematic, strawman schematic of it. In fact, this case is a laser-driven plasma collider, but it looks somewhat similar for beam-driven. There are a bunch of challenges. I'm not going to have time to go over all of them today. I'm going to focus on three. I'll talk about positron acceleration, staging, and beam physics. So let me start with positron acceleration. Okay, so I showed you this picture before. The electrons, they can be situated here, and they can all see the same accelerating field, the same focusing force, and get accelerated. And where do the positrons go to achieve that same thing? There's basically this tiny region that's focusing and accelerating for positrons, but in fact it's quite non-uniform. This region, there's basically no place for positrons in this type of wake. So we had to invent alternatives to try and solve this problem. How you're going to accelerate positrons in a plasma wake field. So one concept is called the hollow channel plasma. This was my PhD thesis. Another concept is warm plasma channels, where you take advantage of hot ion motion. Another concept is asymmetric plasma channels, which is kind of related to this concept, but you use asymmetric beam drivers. Non-neutral fireball acceleration, where you overlap electrons and positrons in plasma. donut-shaped drivers where you control the flow of plasma electrons in the region of positron acceleration, and quasi-linear plasmas where you sort of try and go beyond this issue of the field being non-uniform by shaping the bunches in just the right way. And so as part of this SNOMAS P5 process, we said, okay, we got a lot of options. We have to since we're still at sort of the design table phase and not the detailed optimization phase, let's just pick one of these schemes and start to design a collider around that. So we had a visiting grad student. Her name was Jevi from University of Oslo. She just defended her PhD thesis last week. And so I said, okay, Jevi, pick your favorite one of these concepts, and then we'll go and we'll design the collider. And she looked, and a week later she came back and she said, these are all terrible ideas. And she said, we should just throw this thing into the trash and get new ideas. And I said, okay, if they are all terrible ideas, can we at least understand why they are all terrible? Do they have something in common? So, yeah. So I've kind of showed a version of this picture a few times now. By the way, these come from particle and cell codes. There's a lot of PIC code expertise here. John Carey's group and CU Boulder has a lot of plasma expertise. But anyway, so all these kind of simulation pictures I've been showing particle and cell codes. And so what you see is you've got an electron beam propagating the plasma, creating this wake, and another electron beam trailing, getting accelerated. You can compare this to a situation with positron acceleration where we did this experiment at SLAC where we had just a single positron beam propagating to the plasma, and some of the positrons in the tail of the bunch were accelerated. And we can ask some questions about the plasma electron dynamics in these scenarios. And so in the electron beam-driven case, the plasma electron trajectory basically flows around the beam, and so it forms this sheath. And one way to think about it is that it sees the entire field of this drive electron beam. So you can just do Gauss's law on a cylinder around that beam, and the plasma electron will flow around it, according to the fields created by that beam. If you want to do this with a positron beam propagating to a plasma, it will attract the plasma electrons first, and those plasma electrons might oscillate within the positron bunch before being ejected. And the thing is that this process is actually quite sensitive to the initial conditions. So if the distribution of positrons here changes a little bit, it actually affects the trajectory of positrons traveling through this bunch. If the distribution of electrons here changes a little bit, you kind of don't care because you're just flowing around the integrated charge of that bunch. Okay, so we wrote a review article summarizing this concept and how it relates to all those other concepts that I showed. And we have this thing called the electron motion challenge. It's basically the fact that the electrons are mobile and will rearrange themselves to cancel out the charge of the beam. That's another way of putting it. But there's a particular formulation of this electron motion challenge which is useful when thinking about colliders. So we made this sort of summary plot with all the different concepts that we looked at. On this axis is the accelerating field. So we want to be at maximum accelerating field. And at this axis is this luminosity per beam power, how much physics you can get out of your machine at a given power. And you want to be basically in this part of the graph in order to, one, be a high gradient accelerator, and two, be a high luminosity accelerator. And what you can see is that all these different positron concepts basically fail by 2 to 3 orders of magnitude based on this electron motion metric. But in fact, there's one that doesn't quite get there, but it's a little bit better. So we should focus on that one. We should turn our attention to that one. This is called the finite radius channel. So basically what we're doing in this case is we're controlling the convergence of these plasma electrons back on axis to make this stable accelerating region for positrons. And there's this experiment that we're doing at SLAC to try and demonstrate this. So basically what we need to do is we need to make thin filaments of plasma. We use Bessel beams to create these thin filaments of plasma. Then you have to align the beam to the plasma, and that's hard work. And hard work gets assigned to grad students. So Valentina is one of Mike Lidos's grad students. She's here at CU Boulder. She's been leading this effort to try and align and understand and create algorithms for for just getting the electron beam through. We don't have the positron beam yet, but just getting this electron beam through the plasma. And so this is well underway. We're making progress. It's an exciting direction for our field. And eventually, we want to sort of get that last order of magnitude in luminosity per beam power by optimizing this process. Okay, so I covered positron acceleration. Now I want to cover staging. So staging means you have a bunch of plasma accelerators. How do you connect them and transport the beam through them? So I mentioned at the beginning there's this new concept. It's called half. So it's a Higgs factory that is asymmetric. It's asymmetric because it's avoiding this problem of positron acceleration plasma. We think we know how to do electron acceleration plasma. That's this part of the machine. And we're going to make very high energy electrons, 500 GeV electrons, and positrons are accelerated by a normal conducting linac and collide the low energy positrons with the high energy electrons. And what this gives you, when you collide 500 GeV electrons with 31 GeV positrons, you get collisions at 250 GeV center of mass. They're boosted, meaning that all the collision products move in a certain direction. And there's precedence for this. Babar at SLAC is a boosted machine. Super Keck-B in Japan is a boosted machine. Hera, a boosted machine. So we know how to build detectors for boosted machines. Okay, and so my colleague Carl Lindstrom has been doing most of the design and optimization. It's a fairly small facility, 3.3 kilometers for a Higgs factory, so that's pretty good. But the actual plasma acceleration part is actually a much smaller part. It's just 500 meters. And what he's trying to understand now is all the trade-offs between, should we make the facility smaller, or maybe it's actually better to make the RF linac longer, operate at low gradient, and how do you get this sort of staging of these plasma accelerators to work? And so this is an evolving concept. And so we had this meeting in Arice, Sicily, where he presented a new design with these undulating delay chicanes to get the timing of the drive beams and the witness beams quite lined up. And I think anyone looking at this will say, boy, that looks complicated. And it is. And so the task now is to understand basically the tolerances. How would you build this? How stable would it have to be? How much control do you have over something like this? And Carl's hard at work at understanding how to do this, implementing things like plasma lenses and higher order optics to do corrections. He's got updated designs that include both traditional optics and plasma lenses in order to achieve what we need to achieve. And these designs work equally well for laser-driven and beam-driven plasma accelerators. And I'll come back to this program that we're doing at SLAC right now. This is really the direction that the field is moving. To actually build a demonstration of something like this. We have two plasma accelerators staged and show in detail that you can preserve the quality of the particles through this process. Okay, so that was staging. Last thing I want to talk about is beam-beam physics. So the beams collide, but at very, very high collision energies, interesting things happen. Okay, so when we explain high-energy collisions to the general public, we say, okay, an electron and a positron collide, and then they produce a Z boson and a Higgs boson, and that's what we're going to measure at a Higgs factory. And the thing is that the cross-section for this process is very small. So this almost never happens. And so what actually happens is you're colliding bunches of particles, and the particles inside the bunches see the field of the opposing bunch, and they radiate because the fields are very strong. So that process is called Beamstrahlung, the radiation of particles. And that modifies the energy of the colliding particles. So rather than having them all collide at exactly the energy you want them to collide, a lot of them are colliding at a much lower energy. So we looked at this problem for the 10 TeV collider. This was actually for a 15 TeV collider. And what we find is that what you sort of want in this luminosity versus energy plot is a delta function at the energy of your collision. But really what you get are these very spread out energies of the colliding beams, and this effectively reduces the luminosity of your collision. Not only that, things can just get super duper weird, where you're generating so many photons through this process, and those photons are then interacting with the field of the opposing beam and generating electron-positron pairs. And all of a sudden, you're in a situation where you have more electron pairs generated than you had electrons and positrons in your collision in the first place. And that is really hard to model. So one of the things that we are working on, so this is in collaboration with the WarpX team at Berkeley Lab, and this is from my colleague Ariana Formenti, is new tools for modeling this process. There's a standard tool called Guinea Pig that's been around for a long time. It's single CPU. It's maintained by one guy who's a great physicist, but he's just one guy. And so we want to, develop, a new high-performance code for doing these types of simulations that can also address these future problems of these very nonlinear QED scenarios where pair plasmas are important and it modifies the property. And moreover, we're going to provide a service. So this is the goal is goal-oriented, 10 TeV collisions, but we're providing a service to the community in the near term by providing a robust, high-performing tool that can be used for Higgs factories in the near term. Okay, I've gone this whole talk talking about 10 TeV colliders, and actually not even really talking about like the physics of why you'd even build one. This is a weird place to introduce it, but it's relevant because this beam Stirling problem is really hard. So the beam Stirling problem is really hard because when you collide these charged particle beams, they're going to radiate and lose energy. And so you could maybe start to ask questions, are there alternatives that kind of solve that problem? Are there ways we can get around this energy loss through beam Stirling? And so what the muon collider people say is that muons, because they're heavier particles, they're bent less and they radiate less in the collision, and they're right. And what that means is that they get more luminosity at the desired collision energy, which is great. But there's this other weird thing that's going on, which is that these elementary particles, whether they're electrons and positrons, or muons and muons, or as it turns out, electrons and electrons, or photons and photons, become sort of a composite particle. They're carrying these fields with them. The W and Z boson mass is sort of a small fraction of the collision energy at these very high energies. So they can radiate W and Z bosons just as you would radiate a photon at these high energies. And what this means is that most of your physics is not coming from the collision of a muon and a muon, or an electron and a positron. It's coming from the collision of the W and Z boson to some other particle, even though you never had them to begin with. It's weird. Thanks quantum mechanics, I guess. Anyway, the takeaway here is that a 10 TeV linear collider does not have to be an electron-positron collider. So, So what we're proposing, one of the things that we're proposing, is changing our electron-positron collider into a photon-photon collider. So photons don't have this beam Stirling problem where you have to worry about the deflection of particles in the strong field of the opposing beam. And so if you convert your electrons to gammas by colliding them with a laser pulse ahead of the collision, then you can end up colliding the photons at very high energies and then producing massive particles from that collision, which is pretty neat. And so, with my colleague Tim Barklow at SLAC, we have a discussion of this on challenges with ultra-high energy beam Stirling and beam delivery systems. Okay, so I said that we avoid beam Stirling, which is true, but there is no free lunch. These Compton scattering events have a lot of nonlinear QED going on that we also don't fully understand, and there are these higher order processes that are not well modeled. So this actually is an ongoing area of research. We think that if we collide these very high energy electron beams with free electron laser pulses, KeV photons, we can avoid some of the problems that you might occur colliding it with whatever, 500 nanometer pulses, something like that. Anyway, so this is another direction of our research. How much time? Not a lot. Okay. All right. So I showed you facet at the beginning. This is facet 2. Facet 2 is smaller than facet. It's only 1/3 of linac, but it's still better. It's better because we have even better control of our bunches at facet 2 than we had at facet 1. We got more bunch compressors, which means that we can make even shorter bunches. And ultra short bunches means that we can have ultra high peak current in extreme fields. And so we are doing this right now at Facet, and we're creating these really intense bunches, and then we send them through our diagnostics like a wire scanner. So a wire scanner is a piece of metal that you move through the beam, and when the beam hits it, it scatters some photons or whatever, which you detect in a PMT, photomultiplier tube. And what we find is that after a few iterations, our beam has sliced completely through our wires, and then we can't measure the beam properties anymore. So we say, okay, well, we're not going to use our wire scanners. We'll just send it into an OTR foil, a piece of metal. When the beam goes through the piece of metal, it reflects basically some light, transition radiation, into a camera. And then the beam drills through the radiation, through the foil in a few shots. But okay, you can move the foil up and down. So you can make this work for a pretty long time. It also fails because there's another effect called coherent transition radiation, which totally swamps out your normal OTR signal. So this is also quite a challenge. But then you can have another device called a YAG crystal where it just lights up and you can view it from the backside so that you don't get this coherent transition radiation. But of course, we eat through those pretty quickly. So it's a really fun experiment because we've got this absolute monster of a beam. We can't diagnose it. So we're getting very creative. We got all these like machine learning tools and non-intercepting diagnostics. But on the other hand, this is exactly what we want because the high fields that are destroying these diagnostics are the high fields that we need for these experiments. And they're basically demonstrating that we're getting more control over the longitudinal properties of the beam. And these new generations of test facilities, what they're really doing is providing control. So in 2007, for like the early experiments at SLAC, it was much like the one I showed at the beginning, where you have this long tail of electrons. So it's exciting for accelerating single electrons, but not bunches. And then Mike's work at SLAC in 2013 and 2014 showed that we can actually do this two-bunch process. But you know, the width of this of this beam, the energy spread of this beam, probably not quite good enough for most applications. And my colleague Carl Lindstrom has now sort of drilled this down to a science where you can really get, you know, sub-percent level energy spreads. And now what we're trying to do is exactly this at Facet, but at higher energy and with energy doubling. All of these trends in terms of our efficiency and the energy spread of them, they're going in the right direction for what we need for colliders. So all the trends are in the right direction. We think that we have a real R&D path for these future colliders, but there are many more challenges. And especially, you know, taking the result that Carl got and extrapolating it to Facet 2, where we want to do this from, you know, 10 to 20 GeV, not an easy task. But that's our main thrust right now. Let me just mention a couple other things, and then I'll wrap up. These plasma colliders, they're sort of far in the future still. They probably make the most sense if they follow some other linear collider that's already been built. But we've been doing research on these plasma accelerators for a long time. It'd be good to put them to use. So the easiest thing that we know how to do with the plasma accelerator is to do this sort of accelerate a long tail of electrons, which I just said in the previous slide isn't super useful. But actually, there are people who'd be interested in this. So one example is this LDMX experiment at SLAC that wants to search for dark matter particles. But what they really want is they want a single electron delivered to their experiment at a rate of, you know, a gigahertz or something like that. And so we can accelerate single electrons to very high energies out in this tail here, and we can just collimate away everything that's not there. There are some real challenges in doing this at a gigahertz. You need sort of plasma sources that can refresh fairly quickly. You're also going to be putting a lot of current and power down these lines that has to be handled correctly. But I think this is one example, and it's something that I'm pushing for at SLAC, where we can say, okay, here's how plasma acceleration can extend the reach of a dark matter search. Another example that I'm really impressed with was there's been a series of papers on free electron lasers driven by laser plasma accelerators. And the Berkeley team is sort of the most recent addition to this field where they've done this demonstration. So they have a laser, they shoot it into plasma, they accelerate electrons, and then they put it through an undulator to generate radiation as a free electron laser. And the key here is reliability. So they work really hard to reduce this shot-to-shot jitter as much as possible. And they've been very successful. And this presentation was at the AAC conference in Chicago earlier this year. And they ended with this funny plot, 11 consecutive days with gain. So basically, they've gotten the system to the point where it's acting like an accelerator as opposed to an R&D project. And of course, I'm very excited about accelerator R&D, but ultimately it has to be a useful tool. And so this is a great example of converting this new technology into a useful tool. And he also adds that they still have more work to go. This gain curve hasn't saturated, so there's still more work to be done. Also add, Chris Doss is a postdoc on this project. He was a PhD student here a few years ago. Okay, so I'm done. Advertisements. We have this design study, which I talked about for a while. We're seeking input from HEP theorists and experimentalists because we think there's a lot of open questions here. And if you're interested, I guess I'll have Mike send around a link or something. And you can click and express them. And we have 3 postdoc positions. I basically only got to talk about this topic today, but we're looking at beam effects in circular colliders, some really interesting topics for FCC and EIC, and this position on a compact positron source, which is interesting from a cold plasma perspective, because we're making a cold plasma of positron for that. Okay, yes, so 10 TeV Wakefield Collider Design Study. It's sort of the P5 mandate. We're going to do it. We're going to come up with some sort of concept that we can then make a real R&D path to achieving, and we'd love for anyone interested to join us in that effort. Some of the stuff that we're doing to achieve this 10 TeV Collider Design Study is synergistic with the pursuit of Higgs factories. So these new codes, that's one example. There's another topic I didn't get to talk about, which is using lasers to collimate beams. Beam collimation turns out to be a really hard problem. So having a collimator that, these physical collimators get destroyed by the beam. So having a collimator like a laser, which doesn't get destroyed, is an interesting idea. And we're going to look at this at Facet. And then the third issue is, if you take the P5 report seriously, one of the things that you can, and you understand our field, is that we don't actually have the accelerator workforce to do R&D for a muon collider, to do R&D for plasma collider, to build the Higgs factory, to build the magnets. Those people don't exist. And so there's a lot of people in HEP who recognize that the future of collider physics is more strongly tied at this instance to the lack of accelerator technology. So we want to make it easier for HEP experimentalists who work on detectors to get involved with accelerators. And the way that HEP started, those were the same people in the beginning. It was the accelerator people and the detector people were the same people. There's been a split. And so now we sort of need to recombine in order to achieve these next collider goals. Okie dokie. Thank you. So this is the team at SLAC, and occasionally we know how to have a good time. Yeah.
Thank you, Spencer. Okay, we have time for some questions. So I'll run over and give you the mic. We have some questions. Yeah.
Yeah, no, I didn't quite understand the business about the limited radius plasma. You have the plasma filament, right? And then you inject the beam in, and you make the plasma filament with a vessel beam laser, I guess. And then why did that end up being, what's the critical issue on why that ended up being better compared to the other 6 concepts?
Good. Okay. So the short answer is that the plasma electrons transverse the region where the positron beam gets loaded with transverse momentum. So they carry their transverse momentum through the region, and they're not captured by the positron beam in that region. So you don't have this problem of these positrons then wiggling, these plasma electrons wiggling through the positron beam. They basically converge and go back out. There's a downside, which is that because they carry away some of their momentum, you don't extract that energy. So you create this uniform focusing field that, as far as we can tell, works for low emittance beams, but it's not as efficient as you really want it to be. And that's why it doesn't rank, all the way up on that chart. It's a little below. So we are still trying to find a way to recover more of the energy from the plasma. If we could do that, then this would be a viable concept.
If I may, you also elongate the region of the plasma electron convergence on axis. So there's a larger region in phase space where you can load in a positron beam. So it's a wider target to hit in some sense. Any other questions? Okay. Of course, you're on the other side of the room.
Yeah, thank you for the excellent talk. So I have a question, maybe two questions related. So one is how efficient are these, right? Let's say somebody wants to run 1 gigahertz, like you said, source. Like how much power would this device consume? Is it like megawatts or something?
Yeah, it's a good question. So where did I put that? Okay. Efficiency. So efficiency is an important question for two reasons. One, it determines how much wall plug power that you consume. So if you want to run a high energy particle accelerator, but it takes like a gigawatt of power, that's a problem, because a gigawatt of power is a lot. Also, if you're not very efficient, that means that you're leaving energy in the plasma, and you have to deal with that. So even at something like 50% efficiency, a lot of energy gets left in the plasma. And that's an unsolved problem at the moment. There's basically two ideas that people are playing around with. So one is that you operate in sort of a burst mode, where you run bunch trains through the plasma, and all of the energy is deposited in a relatively short amount of time. And then you have a long time between trains with which to get rid of that heat somehow. Unsolved problem. Or you have something like a gas jet, and the beams are further spaced apart, and the energy that's left in the plasma sort of gets carried away because it's like a refreshing gas jet. So anyway, these facilities optimistically at 10 TeV, hundreds of megawatts. Is it hundreds the difference between 100 megawatts and a gigawatt is a really big difference, like in terms of like the infrastructure needed for that. So we really want to be closer to 100 megawatts, and that's hard, but that's where we're aiming, let's say.
Thank you. So the other question I have is, so if you have a Higgs factory, what's that useful for other than studying Higgs? Is there something else people are after?
Yeah, so the Higgs factory physics program is sort of divided up into a few stages. If you long time.
Is your thumb tired yet?
Yeah. There you go. Okay. So these red curves are the CERN and Chinese Higgs factories, and these points correspond to different physics operation modes. So 90 GeV for the Z boson, 160 for WW, 250 for Higgs plus Z, and 370-ish for TT bar. And the overall physics program is meant to push the standard model to its limit, so to constrain, every possible branching ratio and every possible production mechanism and the width of the particle, and just look for cracks. And so if you say, just study the Higgs, I think what they would say is, poke and prod the standard model in every way conceivable at this energy scale.
Other questions? No? Well, it's still 5 minutes to 5, so you still have to wait here for another 6 minutes. Might as well. No, I'm just kidding. Maybe for once we get out of here slightly early, you guys can really thank Spencer for that. So let's thank Spencer one more time. If there are any other faculty members who'd like to join us for dinner, we're probably going to be heading out shortly. So just come on down and let me know. Everyone else, see you later.